Let's go through this exercise then, using the 11-step guide. First of all, step 1 is your design objectives. Well, this is specified as life safety, and it's specifically to maintain a clear layer height above the height of the people who may have to pass under it. And as this is a public building, the clear layer height should be at least 3 metres. However, in this case, it's also desirable that smoke should not be allowed to enter any shop unit. And the highest shop unit is 3.1 metres. So with a clearance of 0.5 metres, which is what you'd normally achieve, we need to increase the clear layer height to 3.6 metres. So that is the design objective, a 3.6 metre clear layer height. Let's move on to step 2 now, determining your design fire size. Now, we're told that we're using standard response sprinkler heads in this building, so it's convention to assume that the largest size a fire can grow to is 5,000 kilowatts. Don't forget, if there'd been fast response sprinklers, then the design fire size would have been half of that, 2,500 kilowatts. It's 5,000 kilowatts. And with normal sprinklers, you would assume a physical size of the fire, 3 metres by 3 metres, and it's got a perimeter of 12 metres. Again, if there'd been fast response sprinklers, it'd have been 5 square metres with a perimeter of 9. That's what you needed to work out. So we know our design fire size now. Yeah, it's 5,000 kilowatts and the perimeter is 12 metres and it's 3 by 3 metres. So now we know the design fire size, let's work out the mass flow rate of smoke. So determining the mass flow rate of smoke. Now this is a single storey mall and the smoke leaving the shop will flow directly under the spillage into the reservoir. Therefore we need to use a spill plume model. The obvious model to apply is the single-storey mall model. However, you've got to ensure that the model's valid first. And to be valid, the smoke cannot rise more than 3 metres before reaching the base of the smoke layer. Now in this case, we've already established that the clear layer height will only be 0.5 metres from the spillage, so you know straight away it's valid. It's going to be 0.5 metres from the spillage, so this you can use this formula, and this is the one here. M smoke equals CE P Z to the 1.5, where M smoke is your mass flow rate of smoke, CE is your coefficient of entrainment, P is the perimeter of the fire, and Z is your clear layer height. So let's put in the variables. Now the coefficient for a single storey mall is 0.38. Using this formula, single storey mall with a low height of rise is 0.38. So that's the coefficient you'd use. And the perimeter is 3 plus 3 plus 3 is 12. And the clear layer height is 3.6 metres. If you'd have put them in, you'd have got a mass flow rate of smoke of 31.15 kilograms a second. So now we know how much smoke's been produced. Now we know how much smoke's been produced, we need to know how hot it is. We need to move on to step 4, which is determining the temperature of the smoke. This is the formula to apply. Theta equals QP divided by MC, where your theta is your temperature rise, your QP is your convective heat output, M is your mass flow rate of smoke, and C is the specific heat capacity of air. Putting your known variables in the formula, you'd have got a theta value of 159 degrees Kelvin. So it's quite a high temperature, 159 degrees Kelvin. Now we need to work out the absolute temperature of the smoke using this. TL equals T0 plus theta, where your TL is your temperature of your ambient air and theta obviously is your injured increase. Put that in, you'd have got a TL of 447 degrees Kelvin. Now it's important to remember at this point, because this is a life safety system, the temperature of the smoke cannot exceed 200 degrees C. So we've got to convert this temperature now from Kelvin to C. So what you do is 447 minus 273 gives you 174 degrees C. So although this is very hot smoke, it doesn't exceed tenability and you can accept it. It's not over 200 degrees, so it does satisfy the design criteria. Let's move on to step 5 now, the stratification check. Now in this case, because the clear layer height is so low, in other words 3.6 metres, then stratification can be ignored. Stratification only applies to very, very high rises of plume. Not high enough, you don't have to carry out the stratification check. You can move straight on to step 6, which is determining the ventilation requirements. Now it's been decided to use natural ventilation, and therefore we will proceed with that in mind, natural ventilation. The first thing you need to determine is the number of reservoirs in the atrium. Well, this has been specified for you. They've told you there's 2 reservoirs, 6 metres by 60 metres. The 60 metres is the maximum size you can have on any dimension of a reservoir, 6 by 60. Now we need to work out the area of ventilation required in each reservoir. We know how much smoke is being produced. Now we need to know how much area of ventilation is required in each reservoir to maintain the clear layer height of 3.6 metres. And this is the formula you need to apply, the AVCV formula, which we've used during the course, this AVCV. Now, if you put in all your known variables in there, you'd have got this. Now, one thing to remember on here is when you got to your AVCV, AICI, there, you've only got two reservoirs. One is coming in and one's coming out. So what I'm getting is the air provided can come from the other reservoir. That's why in there you'll see 1 divided by 1. The AVCV, if you put all your known variables in, you'd have got an AVCV of 8.8 square metres. So we need at least 8.8 square metres of aerodynamic area in each reservoir. Now that covers this step. Let's move on to step 7, which is determining the number of ventilators then. Well, we know what total area of ventilation is required, 8.8 square metres. Now this is aerodynamic free area. In other words, you've got to take into account the efficiency of the ventilators. And they're generally about 0.6% efficient. So in other words, they're normally 60% efficient. You're not going to get the whole area extracted, about 60% efficient. So if you divide 8.8 divided by 0.6, you get 14.67 of geometric area. So that's what you actually need in each reservoir, 14.67 metres squared of geometric area. And don't forget, ventilators don't come bigger than 6.25 metres, so we need at least 14.67 divided by 6.25 gives you 2.347 or 3 ventilators. That's what you'll need, at least 3 ventilators, the absolute minimum. So where do we locate this? Well, before you can decide where you locate them, you've just got to carry out a stagnation check. Now this only applies to natural ventilation, and it means ventilators cannot be more than 10 metres from the edge of the reservoir and no more than 20 metres apart. And this is because the smoke may stagnate in between. If it's too far apart, it may stagnate in between and start to drop. Now, if you look at the reservoir, it's 6 metres by 60, and mark a line at 10 metres and 20 metres. As you can see here, this shows us where we need to install them. And based on these dimensions, as you can see here, you're going to need at least 3 ventilators located on these lines, somewhere on those lines, to maintain the 20 metre gap. So you need at least 3 ventilators to satisfy the stagnation. Well, as it is, you needed 3 anyway to meet the volumetric the flow rate. So in a way, it matches up. So the answer is you will need 3 ventilators located, as you can see here. That's what you need, 3 ventilators. So we need 3 ventilators with a total geometric area of 14.67. So each one will have an AV of 4.89 metres squared. That's what we need. Now that covers step 8. Let's move on to step 9 now, which is the plug holing check. Again, this applies to both natural and mechanical ventilation. We've got to make sure that it's not going to plug hole. Now don't forget, there's 2 models to determine if plug holing will occur, and this will depend on where the ventilator is located. Basically, there's one if it's less than 2 metres from the edge and one if there's more than 2 metres. Well, in this case, the ventilator will be more than 2 metres away, so this is the formula to apply. mcrit equals 2.05 times rho naught times g TO times theta to the power of a half times d squared WV to the half, the whole lot divided by TL. Now, to work this out, you need to work out your WV factor, your width for the ventilator if it was a circle. And this is the formula to convert your ventilator into a circular one. And it's WV equals 4 times AV per vent divided by pi to the power of a half. Now, if you put in your known formula, they've got WV equals 4 times 4.89. Do you remember we said before it was 4.89 was the geometric area of each ventilator? Divided by 3.142, and the square root of that, it would have given you a WV of 2.495. So you've got all the variables you need. You should have inserted them in the plug holing formula. As you can see here, you'd have got an mcrit of 75.51 kilograms a second. That's a lot of smoke that it can extract before plug holing based on the parameters you've inserted. 75.5. Now we need to ensure that the smoke lead does not exceed this. Well, we know the mass flow rate to be extracted earlier was 33.1, and we've got 3 ventilators. Therefore, the maximum leave in each ventilator is 11.03 kilograms a second, which is well below the mcrit. So in this case, we know we're confident plug holing is not going to occur. Now that completes this step. Let's move on to step 10, which is the air inlet check. Now, the air inlet check only applies really to mechanical ventilation, not to natural. You're never going to get a system where the natural ventilation is drawing in that much air that it's going to cause a problem with the means of escape, the velocity. So in this case, you don't have to carry this check out because it's a natural system. This brings us on to step 11. In this, you're going to consider the effects of wind and if there's any tall buildings. In other words, you might want natural ventilation, but you might work out actually, based on wind direction and the wind strength or the location of other tall buildings, that you might not be able to have natural ventilation. You might have to go for mechanical. So you work that out in this step. That was step 11. And that concludes this exercise.